a function to model a variable in terms of another variable to make a prediction, right, in practical situations, okay? So practical situations is really these like real world situations we're going to be looking at, right? So we're kind of now connecting all of this to the real world. Okay, so really where we're going to start is just kind of thinking about how, when we hear words, we change them into mathematical expressions. So for example 1, we are going to write all of these as expressions. And remember, an expression is something that does not have an equal sign, and therefore you are not solving anything. Oops. Again, expressions do not have equal signs, and therefore we are not solving them, right? Or just saying this is an expression. Okay. So looking at A, we're going to do 5 less than twice a number. Okay. Well, this number is always like my variable. I'll call that X. So I want to do 5 less than that. So I know I'm going to be subtracting 5. But I'm going to be subtracting 5 from twice that number. So twice is 2x minus 5. Okay, so I took twice the number and then I subtracted 5 from that. Looking at B, a number decreased by 6, then doubled. Okay, so again, a number decreased by 6, then doubled. Again, X is our number. And I am decreasing that by 6. So again, I'm going to have a minus. So I should have X minus 6. I'm doing that first, then doubling it. So sometimes the order of what you're doing matters. Here, I'm taking 5 less than twice the number. I did twice the number first and then took 5 less, right? Here, I'm subtracting first and then doubling the whole thing. Okay, so be very careful to the order that it's asking you to do things in. Okay. Looking at C, we have a small company has $1,000 to distribute to its employees as a bonus. Write a mathematical expression for how much money each employee will get. Okay. So my expression is going to represent how much money each employee will get. But I probably still have an unknown. Okay. What is this going to depend on? Well, if I have $1,000 and I'm distributing money to each employee, how much they get is going to depend on how many employees I have. So my variable is going to be my number of employees. Okay, because how much they each get will change if I have more or less employees. So I have $1,000. And each employee right, is going to get some of that money. So I'm going to divide it by my number of employees. Right, so 1,000 divided by X will represent how much they get. Okay, looking at letter D, a salary after a 4.4% increase. Okay. Well, again, I want to know what I want to know what the new salary is going to be. Okay, and what is my new salary going to depend on? Well, it very much depends on what my salary is right now, right? I don't know what the new salary is going to be if I don't know what my current salary is. So again, we have to let that be our variable. I guess this is really our current salary. And then we want to know what like the new salary is going to be. Well, if I'm getting a raise, I get to keep all of my old salary. And then I'm getting this 4.4% increase. So we don't use percentages in our mathematical equations. 4.4% is the same as 0.044. Remember, you move the decimal place twice to switch from decimals to percents. Okay? So I get to keep all of my old salary, plus I get another 0.044 of that same old salary. Okay, so I'm increasing it. These are like terms, and when I add them, I get 1.044s. Okay, so if I increase by 4.4%, my new salary will be 1.044 times my old salary. All right, moving on to example 2. Now we're writing equations for each of the following. So equations have an equal sign, right? It's right in the name, equation, right? Equal sign. All right, looking at A. One leg of a right triangle is 3 times as long as the other. Write the length of the hypotenuse as a function of the shorter leg. Okay? So this tells me what it wants my variables to be. I want to write my hypotenuse. So I'll say let H equal the hypotenuse. And it wants it written as a function of the shorter leg. So we'll let S equal the shorter leg. So this is talking about a right triangle. So I'm going to actually draw a picture because I'm not really quite sure what I'm going to do. So let's draw a right triangle. Right? I know my hypotenuse is here. And without worrying about it too much, I'll say that's the shorter of the two legs. So I need to know what this other thing is going to be over here. Well, it does tell us that one leg of a right triangle is 3 times as long as the other. Right? So if it's 3 times, then it is going to be bigger. So that's our missing piece here. It's 3 times our shorter leg S. Now I want an equation that relates these things. So a lot of times with these, we have to think back to things we've done before. Well, if I have a right triangle, then I know I can use Pythagorean's theorem. Remember, a squared plus b squared equals c squared. So I'm just going to put my variables into this equation. So I have s squared plus 3s squared equals h squared. And now what I want to do is since I want it as a function, right, I want the length of the hypotenuse as a function of the shorter leg, I want to get h by itself. Okay. So I'm going to simplify this. I have s squared. Well, again, exponents like distribute in, so that's 3 squared s squared. Equals h squared. So I have s squared plus, well, 3 squared is 9 squared s squared. Not 9 squared, just 9. Okay. 9 s squared equals h squared, right? Just by squaring that 3. So s squared plus 9s squared. So I'm going to combine these, right? S squared plus 9s squared is 10 s squared equals h squared. And then I'm going to take the square root of both sides because I'm solving for h. So I need to take the square root of 10s squared is going to equal the square root of h squared. I do that because my square root and my squared cancel, so I'll just be left with h. Well, when we're doing square roots, we want to make sure we can't, if we can simplify it or not. And this we actually can simplify. Because if I split it up like this, right, s squared is a perfect square. What's the square root of s squared? And the last thing I'm going to do is I'm writing this as a function. So h as a function of my shorter leg equals s square root 10. So we just change it into our nice function notation. Okay, let's look at B. Something very similar, right? Again, we're going to be given a situation and I want to create this equation from it. So the diameter of a right circular cylinder equals half of its height. Write the volume of the cylinder as a function of its height. Okay, so again, I know I need to use volume. As a function, all right, a function of its height. So I'll have h equal our height. So again, we're talking about a cylinder here. So let me draw a cylinder. I know we're going to use this h, right? I know the height is just going to be h because that's one of my variables. Anything else I need to put in terms of either v or h. I don't want to introduce more variables. So let's think about what we need to find the volume of a cylinder. If you think back to last year, and I know you did this last year because this is literally what we just tested on in 2 honors today, is the volume of a cylinder is pi r squared times height. And so that is our volume formula for a cylinder. So again, a lot of these things that you did in Int 2 honors, Pythagorean theorem, volume, those formulas come back and you kind of just gotta, even if you don't remember them like completely from memory, be able to be like, oh yeah, I can find it. Like I know if I look it up, I'll be able to use it, type of thing. So we have our h, there's this r. Remember, r is our radius. So we gotta look through our problem and see what it tells us. Well, it tells us the diameter is half of its height. So remember, the diameter of a circle goes all the way across my circle. So this whole red line is half of my height. So I am going to represent that by height over 2. Right? So my diameter is half of my height. But my diameter is not my radius, so I'm still in a little bit of trouble here, right? I can't plug in h over 2 for my radius. So now we have to think about, well, what's my diameter? Or, sorry, what's my radius? So then, remember, your radius is only halfway across your circle. So if I draw this nice orange line here, that would represent my radius. So your diameter is half your height, and then your radius is again half of that diameter. Okay, so our radius equals half of our diameter, meaning it's going to be half of h over 2, meaning it's going to equal h over 4. Okay, so our volume then equals pi, I'm going to substitute in h over 4 squared times height. Make it look a little nicer, right? So we just have to plug in, right? We want these 2 variables. These 2 variables are perfectly fine to have. So the v and the h, we don't have to change them at all. We have to change any variable that's not v or h. That happens to be our radius. But now the only variables we have are v and h, so we're good. So I'm going to simplify this so I get v equals pi. Remember, we can distribute our exponents through multiplication and division. So this is the same thing as h squared over 4 squared. Which is pi times h squared 16 times h. And the last thing I'm going to do is multiply my h's. So I get volume equals pi. Well, h squared times h is going to give me h cubed. So I've simplified everything. My volume, which is what I want, by itself is by itself. So I just need to write this in my function notation. I want my volume as a function of height does equal pi times h cubed over 16. Okay. Let's look at one more. Our example 3. A river has risen 8 feet above its flood stage. The water begins to recede at a rate of 3 inches per hour. Write a model that shows the number of feet above flood stage after t hours. Okay. So again, our model is we want the number of feet above flood stage, if I can speak. So we're going to let f equal feet above flood stage and so then t equals time in hours. Right, it does specifically say t hours. Okay, well, what's happening here, right? I have my river is flooded, and then the water is leaving at a constant rate. So my feet above flood stage, my F, is going to equal, well, it starts at 8, right? That's its starting point. So it's at 8 feet right now. In another hour, I'm going to take away 3. Then after another hour, I'll take away another, 3 inches. Then after another hour, I'm going to take away another 3 inches. So every hour, I'm taking away so much. So if I know how many hours it is, I should just be able to do 3 inches times that t. But we have to be careful because it does want it in inches. In feet, right? It's feet above flood stage. So this 3 inches is not great. You can't switch units. Three inches is the same as 3 over, well, there's 12 inches in a foot. So 3 over 12 feet. Which equals 0.25 feet. So I'm taking away 0.25 feet every hour. So So to write this in function notation, my flood stage as a function of my time equals 8 minus 0.25 over that. Okay, looking at B, when will the water be 1 foot above its flood stage? Well, this 1 foot, since it's talking about my flood stage, 1 foot represents your F. So I'm going to use my equation, but instead of F of t, well, I know my output is just going to be 1. I want 1 foot. Equals 8 minus 0.25 t. And now I'm just going to solve for t, right? I'm going to subtract 8. Well, 1 minus 8 is negative 7. And then I'm just left with negative 0.25 t. So then again, solving for t, just dividing by negative 0.25. Those cancel. So I'm left with t equals, and you can always throw that in a calculator, but you do get 28, and then we do want units, and it was 28 hours. Okay. So if you can model the situation with an equation, you can then figure out things that maybe you want to know, right? So maybe you can't start doing things until it's at least down to 1 foot, or maybe, right, you want it down to 0 feet before anything, so you could solve for that, right? So if you can model the function, there's all sorts of things you can do then.